Welcome. Here is some recent work on graph complements of cyclic graphs. It seems simple, but it is related to many interesting topics in mathematics. So the graph complement of a graph is, again, a graph with the same vertex set, but we just replace every edge with a non-edge, and every non-edge becomes an edge. So it's a nice duality in graph theory. And here we see examples of cyclic graphs, like we start with a 5 gon. When we take the dual, we get again the 5 gon itself dual, but afterwards it becomes more complicated. To the right we see always the unit sphere, which is also of interest. This is the graph complement of the path graphs. So you see here they are very regular, they are very symmetric, have diameter 2, and so they look pretty boring, but actually they are very interesting. First of all, from graph theoretical point of view, they are clawless graphs. So the dual has no induced graphs which are triangles. There is a vertex regular, so the number of the graph vertex degree is constant. It's Hamiltonian. All the GNs are Hamiltonian. The GN plus are not Hamiltonian, but the GN 2n plus 1 are Eulerian because the vertex degree is 2n. So it's even by the Euler theorem, Euler-Herholzer theorem. Independence number is 2, diameter is 2. They're very small graphs. The Shannon capacity is 2. And I'm surprised that we can compute the Shannon capacity, while in the cyclic graphs we cannot. For the 7 gon, it's already not known. The Wiener index is exactly known. It's just a sum over all distances, possible distances in the distance matrix over 2. The Harari index, the reciprocals of the distances, which is interesting in chemistry, chemical graph theory. Euler characteristic is known in 6 periodic. So on, everything is known. The Kirchhoff matrix, the Laplacian is 0 Laplacian on 0 forms is a circular graph, a circulant graph. So everything is known by Fourier theory. And but here are some examples of small cyclic graphs and their dual. So the heptagon, that's kind of an interesting case because the dual is a Möbius strip, kind of a nice way to realize the Möbius strip. Then the dual of a path graph here, this is a kind of a prism type. Then we have a dual of a disjoint union becomes the join. So if you take a K2 graph, this becomes a 2-point graph, and if you take the joins of 2-point graphs, you get higher dimensional spheres. In this case, we get the octahedral. So there are many interesting features. So that's kind of this beautiful Möbius strip. That's kind of one of the only cases where we have really manifold with boundary structure. And the 5 gon also is a circle, but otherwise they are actually not discrete manifolds, but they are homotopic to manifolds, and we will come to this. So other examples, so the utility graph is a dual to 2 copies of K3, the Petersen graph, and the dual. The complete graphs produces point graphs without edges. The point graphs without edges become complete graphs. So there's this duality. But the main result, and that's kind of, I was playing with these graphs and was computing the cohomology groups until as far as I could. And I saw always that they appear to be spheres, and actually one can prove this. So these are all these G and these duals of the cyclic graphs are actually all homotopic to spheres. So the maximal dimension is much larger, of course, but the homotopy type is of the homotopy type of a sphere or a wedge sum of spheres. That's in the case when it's divisible by 3. So let's just look quickly at the proof. The proof is quite simple by induction. What you do is you just first of all see if you take the disjoint union of a cyclic graph with this graph with 3, this path graph of length 2, has a dual which is a 0 sphere, and so when you in the dual case, what happens is you get the join. So the join with the 0 sphere is a suspension, so you get a higher dimensional sphere. And the rest, what you do, are all homotopies. You just show that they are homotopies. So what you can do is, first of all, let me just show you that. First of all, you make a connection between the two disconnected graphs, and then you make another connection, and then you delete one of the edges. And so these are all homotopies. So this is actually adding one n, increasing n by 1 is kind of like the cube root of the suspension. After 3 such steps, you get the suspension. Pretty cool. So here we look at the example. So S0, if you take a square, right, the dual graph is just the diagonals. These are two disjoint K2. Gave G5 is self-dual, so it's one of the smallest cases. The G6 is a kind of a prism, two triangles put together. So this is actually a figure 8 graph, S1 cross a wedge S1, a wedge sum of two circles. And then G7, that's what we have seen, is the Möbius strip. Möbius strip is homotopically to a sphere, is a one-dimensional sphere. G8 is already a two-dimensional sphere. G9 is now a wedge sum of two spheres, so kind of a bouquet, sphere bouquet with two spheres touched in together at the point. G10 is a two-dimensional sphere, kind of much fatter already, but still. And then G11 is already a three-dimensional sphere, and so on. That continues like this. The unit spheres are also interesting. The unit spheres are the complements of path graphs. So here we see from G11, the unit sphere is a G8 plus. So this is we lose three points, the point and then the things which were connected, right? They are going away because they were anomo connected afterwards. And and in this case, what we have is we have spheres or contractible points, contractible graphs, which I call points. So that's in the case when we have so these are the cases. And so let's just look at the examples. So G4, that's also a self-dual case where we have a contractible graph. G5, we have G5 plus, that's a house graph, which is homotopic to one sphere. G6 is kind of prism, but with a connection. So in this case, this is actually a circle. It's homotopic to a circle. G7, it's contractible again. G8 is S2. So we have kind of like that. It goes always between contractible and sphere in this case. So one of the consequences is if you have a forest, you can take the graph complement of a forest, and then you have to understand for a tree, you just always get a sphere or a point. And then when you take the graph complement of a forest, you get always a sphere or a point, which is kind of a nice result. And then there is also quite a bit of combinatorics coming in here, so we can count the number of triangles, tetrahedra, and so on. All this what comes into the Whitney complex. And so this is something we can count explicitly. So let me just explain this f function. So from the number of vertices, number of edges, number of triangles, etc., these fk's, we can build a function which is called the simplex generating function, and it will be very elegant to write everything with this simplex generating function. So in the case of the dodecahedron graph, which we see here, which has 20 vertices and 30 edges, so the function is 1 plus 20t plus 30t square. What is nice about these functions is that they multiply under the join operation. And then we have the total number of simplices is just a hyper-Fibonacci sequence, which is very nice. It's the Fibonacci, but we always add 1, so that's called hyper-Fibonacci. And the Euler characteristic, which is the alternating sum out of the fk's, that's the Euler characteristic. This is 6 periodic. You can explicitly give formulas here. And for example, F11, we have 198 simplicia complex with 198 simplices, and then the Euler characteristic is 0. It's actually a 3-sphere. We have seen that the 3-sphere has Euler characteristic 0, like every odd-dimensional manifold. So now these polynomial sets are called Jacobs-Tal polynomials. Of course, they were not introduced in this context, but it's a nice way to write the recursion. There's a recursion which, and then there are explicit formulas like for the Fibonacci number, so you can explicitly write down the nth polynomial. This is a polynomial in square root of 4t plus 1, which is pretty cool. So we have everything explicit. And then I proved the Gauss-Bonnet last year, Gauss-Bonnet version, kind of the most elegant way to prove Gauss-Bonnet, general Gauss-Bonnet in arbitrary dimensions, is to take to formulate with respect to these f functions. And what you do is you take in order to get the curvature at the point, you take the unit sphere and you take the f function of that unit sphere and you take the antiderivative. That gives you the curvature function, and then these curvature functions add up to 1 minus the simplex generating function. So in the case when you evaluate this polynomial at -1, and you get the Levitt curvature, and the Euler characteristic is then 1 minus fg of -1. So the usual Gauss-Bonnet is just a specific point, but it's true for any t. And you see, this is very useful to have that kind of elegant description here. Let me just take the example of the dodecahedron graph, which is a one-dimensional graph. It has no triangles, right? There's a triangle-free graph. So there's 20 vertices, 30 edges, so that's the function. Then the unit sphere consists of 3 points, so the generating function is 1 plus 3t. Integrate that, antiderivative is minus t, and you can take the minus, and minus 3t square half. And then you add that up, you get, add up, they are all the same because it's of the, because of the symmetry, it's a Platonic a graph, and then you have you get the Euler characteristic -10, which is kind of just 2 before the sphere, and then you have 10 holes because these faces, these cells, two-dimensional cells, are not there, right? So this is one of the confusions which is well described in Lakatos. What is really a cell in a polytope if you don't go into realizations, if you do everything combinatorically. So in this case, the curvature is -1/2 at every point. Which is always, say, for trees, it's always you can get it in terms of the vertex degree. In the case of this is kind of also something which is very old, 100 years old at least, in context of graph coloring. When you look at the polyhedra which are triangulated, these are actually planar graphs. And there, the curvature is just 1 minus the degree of the vertex divided by 6. So if every unit circle is a cyclic graph, that's a very special case. And in this case, in that case, I just took a polyhedron, one of the dual the Catalan solid. It's a Catalan solid, and then we have the curvature 1/3 or -1/3 or 0. And the Euler characteristic is 2. Of course, 26 vertices, 72 edges, and 48 triangles. But it doesn't stop with 2 dimensions. It's arbitrary dimensional, and so for a four sphere, for example, when we have an Euler characteristic 2, every even dimensional sphere has an Euler characteristic 2. So there, the curvature is in this case, I generated this sphere as a join of a 1 sphere and a 2 sphere. That gives us a 4 sphere. And it adds up +1 for when you take the join. That's like in the topology. And so the F vector is already pretty large at 288 4 simplices. And so the Betty number you can compute. That's like for a 4-dimensional sphere. Euler characteristic is 2. Everything works like in the continuum. But now comes the real interesting thing. So I was looking also at the curvatures of the dual path graphs, which are the unit spheres of the cyclic graph duals. And so in this case, you see that the curvature actually converges, not to a fixed point, but converges for n to infinity to a 6-periodic attractor, which is very exciting. So that's kind of a stable homotopy type thing. So you go to infinity and you see kind of there's a limiting structure, a differential geometric structure going there. And it's actually kind of we can explicitly give everything, at least, at the limiting functions I could not yet compute, but they are there just for every n, you can explicitly compute it. So in this case, we have n equal to 174. That would be already ludicrous. This is a 57-dimensional sphere. I could not compute the Hodge matrix and the kernels to get all the cohomology groups. I could not do that, or also the curvatures directly compute them, because you would have to compute so much. But in this case, we have recursions for these F vectors, so we can explicitly write down everything. So that's the result. So especially we can formulate it as a renormalization a result when you take barycentric refinement. If you take barycentric refinements, you actually get a periodic orbit of period 6, and so also, when you start with the forest, it doesn't really matter. You get to the same thing. You cannot add a cyclic thing. For a cyclic thing, then that's different, right? For a circle, we have seen the curvatures actually, because of symmetry, is actually constant there. It's not interesting for a circle, but so this is a very nice thing. So here we see this periodic 6 attractor. So this actually what happens is the curvatures actually are built up from different parts of this a sphere or a contractible space. So they are depending on a modulo 6, right? So for k 6k plus 1, the Euler characteristic 1, so the average is 1, and so we have also the Euler characteristic explicitly. So that's the 6 periodic orbit. It's very interesting, and actually generalizes also to other Cayley graphs. As I've seen, there is a similar story like for the dihedral group, and but it's still pretty much unexplored for most of the things. So why does this work so well? Because we have explicit formulas for everything. We have explicit formulas for the f functions. We have explicit formulas for the curvature. Because what happens if you take a path graph, right, and you cut it in two? What happens when you cut it in two? You get two path graphs, and for each path graph we have the simplex generating function, and because they are disjoint in the dual, this becomes the join, and the f functions multiply, and then you take the curvature, which is the antiderivative. So everything is pretty explicit. Now, another completely different thing, but also where some stable homotopy part comes in, is if you look at the Lefschetz story. Lefschetz story is if you look at one of the automorphisms, one of the symmetries of the, and you take one of the symmetries of and let it act on the cohomology groups, and you take the supertrace of that, then you get what one calls the Lefschetz number, and then you can also look at the fixed points. And there is a theorem which is in the continuum pretty heavy, but in the continuum, in the discrete here, is almost obvious. But so I proved that in 2013. Most people look at graphs as kind of one-dimensional objects, right? Only look at the vertices and edges, but the Whitney complex actually allows you to explore higher dimensional simplicity complexes like that. And it's not a big a deal to restrict to graphs, because every simplicity complex which is a Barvcentric refinement is actually a Whitney complex from a graph, and actually all these results are invariant under Barvcentric refinement, kind of going to the continuum. And but the continuum is much heavier, because you have to make assumptions like what kind of maps you take. You have to take either submanifolds as fixed points or individual fixed points. In this case, you don't care. It's everything. It's even true for the identity. Or the identity you get the. Yeah, so here's the theorem. So what you have is you have an automorphism of the graph, and then you have the induced map on the cohomology groups, which is just actually at the kernel of these Hodge matrices. And then you have the supertrace, which is the alternating sum of these traces on the individual blocks. And you have the fixed points, and every fixed point has an index, which is it involves the dimension of the simplex, and also involves the permutation induced on the simplex. I found this all by doing experiments and just seeing what is going on. This is in the case when you have a contractible graph, then only the first cohomology group is vanishing, and all the others are zero. So you will have a fixed point. That's the Brauer fixed point theorem. So here are the Lefschetz numbers. One of the things was also I wanted to see how far I can actually compute these Lefschetz numbers, and it's quite so here we see it until 16. I could go further until 30 or 35, and you see kind of there's a 12 periodicity coming in, and it's actually all clear because of that theorem. Because what happens is you have either you have the cohomology groups have in the sphere case they are just two. In the sphere case, there are just two places, and you can either have 1 or -1. And in the case of a wedge sum of two spheres, you can have either 2 or a ±1. So it can become 1 or ±2. So it can become 3 or -1. So there are these possibilities, and you see kind of what happens. And so these are the Lefschetz numbers. And just something about the cohomology. It's quite a nice thing, and I include in the in many places I've put the code. It's about 6 lines of mathematical code to compute all these bases of the cohomology groups, and the Betti numbers, of course, as the dimension. So in this case, we have taken G9, which is a wedge sum of 2 spheres. And in this case, I plotted here the matrix, which consists of the Kirchhoff-Laplacian, which is the 0 dimension. It's like the 0-dimensional Laplacian in calculus, div grad, and then you have the L1 Laplacian, which is on 1 forms and on 2 forms, and then there's on 3 forms. So 3 forms things, which actually there's no kernel there. So the L2 has a 2-dimensional kernel. So that's pretty cool and very simple in principle to compute. But if the graphs get large, also these matrices get large, and you after maybe 10,000 or 100,000, matrices of that size, you get the square number of entries. So your computer has kind of a limiting amount of memory to store these matrices. That's the kind of limit you do. And just recently, I was looking also at trees and forests. Is one of my favorite things, also topics, because it's related to determinant and pseudo-determinants. If you take the pseudo-determinant is the product of the non-zero eigenvalues divided by the Fredholm determinant, which is 1 plus the eigenvalues, product of the 1 plus eigenvalue, and then you take the limit. In this case, the limit actually for the GNs goes to E. And this is a pretty robust thing. So this actually, whenever you have small graphs of diameter 2, these are all graphs of diameter 2, so this always goes to E, because essentially trees and forests are, when the graphs are getting bigger, and you have much more forests than trees. So it's kind of an interesting thing, and also, in this case, actually explicit, because we have explicit formulas for the eigenvalues. So these are the Kirchhoff-Laplacian in this case. You can also look at the zeta function, which is pretty cool, the spectral zeta function, which is when you take the circle 1 over n, you get the Riemann zeta function. But here we get kind of just for graphs, we get these graph zeta functions. N equal to 5 has this symmetry, which is kind of for all one-dimensional graphs, you have this spectral symmetry, but in general not. And but then the pretty cool thing is that this fraction of forests over trees is actually given as a sum of zeta function values. And you can also compute that for the circle, because everything is well known about the zeta function. If this sum can be computed, I think 2 over pi, or depends on the length of the circle. So you have that also here. So that's, let's mention some open ends. So lots and lots and lots of questions are open. For example, I don't yet know which trees, I know every tree produces either a sphere or a contractible graph. So I don't know yet how to characterize that. So I have to do some more data fitting and things. So take all kind of properties of the tree. I tried already kind of look at the vertex degrees, look at the lengths of the different branches, etc. So there's a rule which it will tell you which ones is a sphere and which ones is a point, but that's not yet done. Then the Wu characteristic, that's kind of there's a story. Calculus and Euler characteristic has all these theorems, Gauss-Bonnet, Poincaré-Hopf, Riemann-Roch, etc. These are all related to Euler characteristic. Then there's a Wu characteristic, which is a quadratic Ising-type interaction thing between the intersimplices. That has a cohomology, has a Lefschetz fixed point theory, as everything is the same, but more complicated and also more subtle, because it's no more a homotopy invariant. So all this cohomology, for example, here we see a 12 periodic Euler Wu characteristic. This can be analyzed, but the cohomology thing I could not even compute that much high enough to actually see a pattern. Then for the Hodge Laplacian, very interesting is the spectral story. So we know the Kirchhoff-Laplacian, that's very clear because of Fourier theory. We can compute all the eigenvalues. We have explicit formulas for the eigenvalues, sine square, n, sum of n square, it's explicit formula, but for the higher forms I don't know. And actually, kind of, if you look at that, by the way, there's this McKean-Singer symmetry, which is pretty cool, that the non-zero eigenvalues of the odd forms and the non-zero eigenvalues of the even forms are the same, because the Dirac operator kind of switches between the two. And but what happens is with the spectrum, it actually seems to converge, kind of the density of state limit, which I cannot prove yet. It's not like a Litsky type thing where you can, like in the renormalization story, which we have covered earlier with a Barvcentric refinement. Here it's kind of a tougher, it seems, but maybe there is a simple way. And here is a picture of the different spectra on different forms. So I took the G18, which is a wedge sum of two 5-dimensional spheres. And then we have 9 different forms. So the Betti number is 100002, right? Because it's a wedge sum of 5-dimensional spheres, and so they are in the 5 forms. There are 2 eigenvalues. This is the yellow thing, and then there is 1 eigenvalue, which is always present in the 0 form, in the Kirchhoff-Laplacian. And then, but you see kind of these 0 forms, 1 forms, and so the 9 forms, 8 forms, the high forms, high degree forms and the low degree forms, they become less and less relevant, because if you look at the F vector, right, so this is a hyper-Pascal triangle, and so what happens is it's kind of essentially like the Pascal triangle, binomial part, but just distorted a little bit. What happens is there are, for example, only 2 eigenvalues of 9 forms, and 18 eigenvalues on the Kirchhoff-Laplacian, right? Because you have 18 vertices. But then there are already 1,782 4 forms, and so this will really, determine this distribution of the entire Hodge Laplacian. And I don't yet know how this is going to work. Also interesting is to look at, these are all circulant graphs. You can look at more general circulant graph in the dual. So what is interesting is kind of, you can look what happens with the Betti numbers, and of the graph complement. Also the self-dual Palais graphs, they are number theoretically given by quadratic reciprocity. You take 2, you connect 2 if they have the same square modulo the number you are looking at here, p equal to 13. And so this is pretty cool. And so they are isomorphic graphs, so they have the same topology. What is the topology which you have here? It's actually interesting. Here you get actually a flat Clifford torus. So this is actually this graph. The curvature is 0 everywhere. So it's in classical mathematics, you would have to realize that in 4-dimensional space, right, you cannot embed a flat torus in 3-dimensional space. And so that's pretty cool here. But that seems to be the end with manifolds, but homotopic to manifolds, but quite complicated in general. And also when you go into higher dimension, when you look at the Barvcentric refinement of, say, a triangle, and you look at the graph dual, the graph complements, the Betti numbers seem to be kind of very, very complicated, and I cannot even go far because of the matrices grow so fast. And that's the end, and I will post something on that. I have written down something. I will post that soon.